Okay, let's take a look at homework 12.3. In this case, I've got a piston cylinder assembly with oxygen and nitrogen starting out at 618 degrees, and then I'm compressing it isothermally to P2, which is 2.36 bar, and then finally I compress it isotropically to T3. And I'm assuming variable specific heats, meaning I need to use the ideal gas tables and mass to determine the following properties. Um, just come over here and take a look at some notes I have on this problem. So the first thing I'm asked to find is the mixture molecular weight. The be the same procedure as in the first two videos. So since I have masses, I can sum the masses. So I have 0.5 kilograms is the total mass, and then I need to find the number of moles. So if I take oxygen, molecular weight's 32. That's m over n, and so I have one unknown. So if I divide the mass by molecular weight, I'll have moles. And if I do the same thing for nitrogen, so I take 0.2 divided by 28, and that's kilogram per kilomole, so I'll end up with moles. And 0.3 divided by 32 for the oxygen will give me moles of oxygen. So then I can do the sum of those and get the molecular weight either by mole fraction or mass fraction. If I do that summation of those the moles that I get, I can put that in the denominator, and then in the numerator I have the total mass, which is 5 kilograms. So when I find the moles of O2, I get 0.00938, N2 0.00714, and then I can come back to this first step and then take 5.5 kilograms divided by 0.00938 and 0.00714, and I'll end up with 30.275. Right, so that gets me through these two. Again, this is just M of O2. Subscript there, divided by molecular weight of O2. That will give me the moles, and M of N2 divided by molecular weight of N2. And then finally, this is just M of the M total, right? The sum of the two divided by N total. Right, the change in internal energy from state 1 to 2. Its change in internal energy is going to be a function of temperature. Temperature of each gas, so the change in internal energy of the oxygen and the change in internal energy of the nitrogen, but the temperature doesn't change, so when I go to the tables and look up an internal energy, I'll get the same value twice for state 2 and state 1 for both gases, and I'll end up with 0 change in internal energy for the oxygen plus 0 change in internal energy from the nitrogen, and the obvious answer is 0. The work from state 1 to 2, since Q minus W equals delta U, since I found that delta U equals 0 from the previous step, then I need to use another equation for that. So I'm going to use the work equals integral P dV, and that's kind of where I start off here. So the work from 1 to 2 is P is equal to MRT over V, And since it's an isothermal process, the mass is constant, the gas constant is constant. So I'll have mRT over V dV, and then take the numerator out of the integral and integrate 1 over V dV, and I get this expression. V2 over V1 would equal P2 over P1 because M R and T are all constants, so they would cancel. There's not a T1 and a T2 in this case. So I can replace that. The only difference is they will be inverted. I'm not sure why I have that. So this should be a negative. One would be a positive, one would be a negative if I flip the P1 and the P2. Anyway, I'll have the right magnitude. The sign would change. So that's how I find work equals integral P dV. The heat transfer from state 1 to 2 will be equal to the work, so equal and in sign and magnitude. So Q equals W if delta U equals 0. Right, then it gets a little trickier. The change in entropy from state 1 to 2. So this is an isothermal process, and the temperature is not changing, so S naught is not changing. So I need to calculate the entropy. Now I know I wrote this out for state 2, 3, but the same would be true for state 1, 2. So I've got delta S total equals the sum of the entropy change for the oxygen and the nitrogen. And the equation for finding change in entropy is the mass times the change in specific entropy. So the mass of each times the change in specific entropy for each gas. S naught is a function of temperature, and so for temperature 1 and temperature 2, those two terms will cancel because they'll be the same value. So we're just left with the gas constant for nitrogen times natural log of P2 over P1, and then the same thing for the oxygen. So we have those two terms. Now, P2 and P1, since the gas composition isn't changing, it's really what we put in this equation for entropy is the pressure of the nitrogen, which is the partial pressure. So the mole fraction of nitrogen times the pressure. But you'll notice, even though I modify my pressure 2 and my pressure 1 by some factor of the mole fraction, that fraction will cancel. So it won't affect when we take the natural log. So you can just cancel that out and just look at P2 over P1. So we have R natural log P2 over P1 for the nitrogen and R natural log of P2 over P1 for the oxygen. Remember that the R is different for each of those cases. And then from that we'll get the change in entropy. So all these S naught terms will cancel. For process 2-3, they don't cancel because we're changing from temperature T2 to T3. In this case, it's an isentropic process. Now, for the process 1 to 2, this is just an isothermal process. The second one is an isentropic process. Let's see. I guess the difference here is that we know that the sum of those equals 0 for process 2-3. So this is not the case for the first one. So there is an entropy change from 1 to 2. For process 2-3, the total entropy change is equal to 0. So this whole thing has to sum up to 0. When we put in all the terms, so you put in S naught state 3 for the nitrogen, S naught state 2 for the nitrogen, so it basically at T3 and T2 we calculate that for nitrogen. Do the same thing for oxygen, S at T3 and S at T2 for the oxygen, so put in those values for S naught, the R for nitrogen, the R for oxygen, and then of course these still cancel for state 2 and 3. Our unknown here is P3, so we'll have this whole term and a P3 in it. Everything else will be numbers. And then this whole term for the oxygen, everything in it will be numbers except P3. And so we have this big expression with one unknown in it, P3, and it equals 0. And then we just solve for P3. So we're going to have all these terms without a natural log. Pull all those on one side of the equation, and you'll have natural log times P3 over P2 left, and then you take the inverse natural log, multiply both sides by P2, and you'll have P3. So you solve for P3 in that case. If you wanted, you can do it with per mole basis. If you're using the tables, remember that S bar is given, and so to use S naught in this equation, if we're doing it based on mass, you need to divide S naught by the molecular weight for nitrogen for these terms, and then divide by the molecular weight for oxygen for these terms. It's a little easier to do everything in terms of S bar, but then you need to use the moles rather than the mass when you calculate delta S bar. And so since I had to calculate the moles, that might be an easier way to do it. And then these values are coming directly from table 823. Right, and then finally when you find the pressure, then you can go on to finding the internal energy. That's just a function of temperature, so you can actually skip step H or part H if you want. And that's just going to be finding all the U bars at the two temperatures, temperature 2 and temperature 3 for each of the gases, multiplying that delta U for each gas times the moles, and you'll have the total change in internal energy. For the heat transfer and the work, for an isotropic process, obviously it's isotropic, so if there's no heat transfer, that means reversible and adiabatic. So the heat transfer is 0, and then the work just equals the total number of moles times the total change in, total change in internal energy per unit mole, or if you have the total change in internal energy, it's going to just equal the work if you've already multiplied times the mass, so or mass or moles. So the Q equals 0 because it's adiabatic. Derived from it being isotropic, and then Q minus W equals delta U. And we already found that. This is U2 minus U1. And Q is 0. So minus W equals delta U, or W equals minus delta U. And I don't have room to write out this expression. That's fairly long, writing out this term for oxygen and nitrogen and solving for P. I hope that's helped. 12.3. I didn't work it all through, but you'll find these equations very useful. They're from chapter 6 of your textbook.